Hello, ladies and gentlemen. We're going to do 12.1b today. We're going to be talking more about limits. Our objectives are we're going to talk about the properties of limits and then direct substitution. So as we get started, let's define some variables. B and C are going to be real numbers, and n is going to be a positive integer. So the first one is if I take the limit of b, if I take the limit of a constant, then that means the limit is the constant. So that's not too difficult. All right, and I wrote these all out ahead of time so we can kind of move through a little bit more quickly. And then this one is kind of what we did yesterday. The limit of x, the limit of some variable, as x approaches c, is going to be the c. Okay. The third one, the limit of x raised to a power as x approaches c, is going to be that c value raised to a power. And I'm not as concerned that you memorize these, but we're going to be using these as we try to find limits of different functions. The fourth one is the limit of an nth root, right? It's going to be the nth root of the constant. So just thinking about if I have a function approaching a certain value, then the limit is going to be that certain value. Alrighty. So now what we want to do is we want to talk about the properties of limits. And basically, it's just ways to think about making a limit easier to find. So if I have two different functions, f and g, and they're both approaching some random constant, then the limit of f is L and the limit of g is k. And again, you don't have to memorize these, but it's just some information as we think about moving through limits. So if I have a multiplier multiplied by a function, then the limit is that same multiplier multiplied by the limit. So you could actually have rewritten this as b times the limit as x approaches c of the function, right? Almost like logarithms, and then it's going to be b times L. Alrighty, the sum or the difference is I could potentially split this into two separate limits. I could take the limit of f, and then I could take the limit of g, which we already had defined as L and k. And so it's just a way of showing you that you could potentially separate these to be able to calculate the limits. All right, the coffee's in the way, travesty. All right, the next one is the product rule. And again, it's the same kind of idea. I could potentially rewrite this as the limit of this function as x approaches c times the limit of this function as x approaches c, and these would just be tools in your toolkit as we try to solve different limits. All right, the next one is the quotient rule, except you can't see it, sad day. You get the next two up there, the quotient rule. Same basic idea. If I needed to, I could rewrite the function, I could rewrite the limits and be able to come up with L divided by k. And then the last property, is the power rule. And if I have a function raised to a power, then the limit, that value, is also going to be raised to the same power. So again, these aren't to be memorized. They are just tools in your toolbox. All right, so now let's start doing some examples. So for the first one, I want to do an example of direct substitution. And life is good when you have a limit problem to do and you can just do direct substitution. So if I want to do the limit of x squared as x approaches 4, there's nothing that makes this function undefined. The algebra isn't tricky. All I have to do is do direct substitution. So this is just 16 because 4 squared is 16. So that's actually pretty easy. Alrighty. So then if I did another one with direct substitution, let's say I want to do the limit as x approaches pi of the tangent of x divided by x. So that could be, if I do my direct substitution, and again, pi goes into the denominator, so it's not undefined, so I don't have to get creative with some algebra. So if I just do direct substitution, this is going to be the limit as x approaches pi, the tangent of pi divided by pi. The tangent of pi is 0, so then therefore the limit is 0. Sorry, one of these days I won't be congested anymore. All right, Remember that you do always want to write a nice polite statement. This would be what you would write in the answer column on your quest to make sure that you don't lose points. Another example of direct substitution is, what if I had the limit of the square root of x as x approaches 9? And since this doesn't have a plus or minus in front of it, we're going to take the principal root, and so then that would be 3. Alrighty. Just a little bit of a detail. This is one of those, you must do this at all times. So I'm going to put note, you must carry, and this is coming from the AP College Board, carry the limit notation throughout the problem until you do your direct substitution. So it's not as relevant today. It will be as we move along through the chapter, but until I can substitute a value directly into the equation to get an answer, I have to carry the limit notation. And by the limit notation, I'm talking about this portion. You have to carry that through until you actually get a numeric value, or until you get an equation or whatever. But you have to carry that notation throughout the problem until you can actually do your direct substitution. Alrighty? Okay, so let's do some that are a little bit more fun. Let's get a different color going here. So let's do our next example. We have a nice short video today, you lucky dogs. So what if I have the limit of x squared plus x minus 6 as x approaches a negative 1? Well, in this one, again, I don't have anything in the denominator. I don't have anything that's going to make it undefined. I don't have anything that's going to make it the indeterminate form. So I can just do some straight substitution. So this is the limit as x approaches a negative 1 of a negative 1 squared minus 1 minus 6. And that simplifies to be the negative 6. And then I would write my answer politely. The limit of the function as x approaches a negative 1 is a negative 6. All right. Next example, and I'll move my paper up in just a sec. For our next example, let's do the limit as x approaches a negative 1 of x squared plus x minus 6 over x plus 3. So again, the first thing that I want to check is I want to look to see if I have that indeterminate form, but this is okay. So then I'm just going to do my substitution. So here's the limit as x approaches a negative 1. I have a negative 1 squared minus 1 minus 6 over a negative 1 plus 3. Do all that math, and I get a negative 3. Write my nice polite statement at the end. The limit as x approaches a negative 1 is a negative 3. So direct substitution is really, really nice because when it works, that means I have less work to do. All right, so here is our last example, lucky dogs. So what if I had the limit as x approaches a negative 3 of x squared plus x minus 6 over x plus 3? So as I look at this one and I think about my direct substitution, that creates a problem down here and the world might explode. So I'm going to try to eliminate the indeterminate form, Indetermin, lovely word, indeterminate form, okay? So I'm going to factor the top. So then this is the limit as x approaches a negative 3. Notice I'm carrying the notation throughout the problem. This factors to be x plus 3 and an x minus 2 over x plus 3. These cancel. So remember, that's called removable VAB discontinuity. And remember, that would also create a hole in the graph, okay? And then I have x minus 2. Now that I've taken away the indeterminate form, then I can do my direct substitution. So this is going to be the limit as x approaches a negative 3 of a negative 3 minus 2, which is a negative 5. Write my nice polite statement. The limit as x approaches a negative 3 of our function is a negative 5. And then we're done for today. That's it. Hope you have a good day, and I will see you tomorrow.